Section 5.3 is dealing with medians and altitudes of triangles, and we actually explored these two concepts today. So we know exactly what a median is, what an altitude is. You actually drew these with some triangles. You probably noticed something happening when you drew all three in a triangle.
They were definitely concurrent.
Yep. So let's just do a quick recap of what a median is, and then we'll do that with altitude as well. But we're going to kind of hit on what's the thing that you should be noticing.
Yes.
So a median of a triangle says it's a segment. Okay, so one way to notice is that it has to be a segment. Whereas with a perpendicular bisector, it could be a
line or a ray.
Same with angle bisector.
Exactly.
So median has to be a segment. That's because it has endpoints that are on the vertex of a triangle and the midpoint of the opposite side. So you guys created these medians today. So if I drew in one, so let's say A is a vertex of the triangle, and let's say the side opposite of that, which is side BC, let's say that's your midpoint. And if I drew in a segment connecting those 2 points, this would be considered a median.
Right.
Okay? And median, a lot of times you think of like the middle of the vertex. So it has to start from the vertex and it ends at the midpoint of the other side.
And we know that it's not a perpendicular bisector necessarily because there's nothing marked perpendicular. It's bisecting a segment, but it is not necessarily perpendicular.
And on the other thing, I like to bring this up, it is coming from the vertex of the triangle, which a lot of times people think it could be an angle bisector, but we don't know if these angles are congruent. So a median has some characteristics of the two concepts we've already seen earlier with angle bisectors and perpendicular bisectors, but you got to be careful with that.
Yeah.
All right. So what we know about medians
is that we have this point of concurrency, which you guys found this in class today as well. And we call that point where all of those medians meet, that point of concurrency, we call the centroid, which to me sounds kind of, I don't know, it just cracks me up. The centroid. It sounds, I don't know, almost a little robotic.
Yes,
I don't know.
It does. It's a weird word.
It is a weird word. The centroid, again, is the point of concurrency of all of the medians of a triangle. And it's also called the balancing point. And, we did this in class today. I had kids, just once they found their centroids, we didn't call it the centroid yet, but I had them just put that pencil tip on that point, and they noticed that they could kind of balance their triangles. And it was kind of a cool relationship. So there's that centroid, that balancing point. It's always...
There's the bell again.
Don't leave. Okay, it's always inside the triangle. Because if you think about it, if you're balancing your triangle, you obviously can't balance it with a point that's outside of that triangle or that's even just on an edge.
Okay. So what did we explore today as well was this theorem, all right? This theorem involves, again, the concurrency of the medians. So the medians will always intersect at a point, and we call that point, again, what?
The centroid.
So the centroid, and that is 2/3 of the distance from each vertex to the midpoint of the opposite sides. Okay, now in this kind of pinkish color, kind of basically sums up what that means. This is kind of our interpretation of it. So if you want to find, if you find the distance from the centroid to each vertex, it is always 2/3 of the entire median. All right, so in other words, in this picture, I have medians, and what gives it away that these are medians?
I can see that the segments go from the vertex to a point on that segment that's across from that vertex, and it is definitely at the midpoint.
And the labeling tells you that.
The labeling tells me that.
So we have three medians, segment AF, segment BD, and segment EC, and they all intersect at a point, and this is, again, called the centroid. So they're saying, let's say P is the centroid. Now, since we have three segments, three medians, we could consider this three different ways. We're doing it one way, okay? So let's say, so the distance from the vertex, let's say A, to the centroid, okay? So that distance AP is 2/3 of the entire median. And the entire median that AP is on is this median AF. So this segment here is 2/3 of that whole entire thing. And we had you guys measure these things today and see that relationship, that ratio simplified down to 2/3. All right. Now, this is what the theorem basically says. But
We know more.
because this 2/3 idea, we actually can say some other stuff. All right. So what if I have the distance of PF? All right.
Well, okay.
That distance compared to, let's say AP, because I'm looking down here. This is going to be, it says a half of this AP.
Okay. Now, which kind of makes sense because I'm looking at that and I'm thinking that if AF is the whole median and if AP is 2/3, well, that leaves PF to be the other 1/3.
Yeah, which is this idea here. I think that's easier to see. So PF is a third of this whole thing.
Right. And if it's 1/3 and then AP was 2/3, then yeah, it's half of it.
Exactly. So this segment here, PF, is half of AP. Now, do you need to know all of these relationships? Not necessarily. If you want to just remember the theorem, the 2/3 idea, then you can use that to help find other things. If you want to remember that PF, this segment from, notice what it is. It's saying from the centroid to the midpoint, this distance is a third of the whole entire median. You can remember that idea. Or you can remember the relationships that make up the centroid. How are these related to each other? Okay, this PF is half of that.
Man, a lot of cool relationships, and this is all dealing with that kind of balancing point of that triangle.
Exactly.
That's pretty cool. These triangles, man, they're amazing figures.
They are.
All right. We also talked today about altitudes. And an altitude of a triangle, it's a perpendicular segment from a vertex to the opposite side, or to the line that contains the opposite side. So when I'm looking at a altitude, you're going to notice that it goes from the vertex, but that it's perpendicular to that opposite side. So you're going to see the perpendicular marked. But notice that it's not necessarily a perpendicular bisector.
Good, okay.
Because it's not bisecting the segment. So it's just perpendicular, but it goes from the vertex. I like to think of an altitude like the height of a figure.
Okay.
Because when I think an altitude, you're talking about how many feet above sea level.
Yeah.
So altitude is the height of your triangle.
And height of something is always going to be perpendicular to a side, and so that would make sense. Now, when it says or to the line that contains the opposite side, what does that mean exactly?
Well, that means that really within a triangle we just have these sides, but that side is technically on a line.
Okay.
So
okay.
there's just no relationship saying that it's bisecting a segment. We just know it's perpendicular.
Okay.
That's the key.
Okay.
That's really going to come more into play when we take a look at some obtuse triangles. Let me
Okay.
just draw one so that way you can see that visual better.
Okay.
So if I had a triangle that looked like this, okay? When I look at the altitude, and technically you could go from any one of these vertices. Please don't think that this is the only
altitude
here.
goes from all three vertices.
Right. But this altitude can go from this vertex, but notice that if I go perpendicular,
It can't
it's
actually
outside the...
It can't actually touch that the side of that triangle, the opposite side,
Exactly.
which we've actually seen before in chapter 1.
We've seen that before. So it's just a way to say that it's, if you would extend that segment of the triangle, technically anywhere on that line where it drops to be perpendicular to it, that's the altitude or the height. Okay. The orthocenter is going to be the point of concurrency of altitudes of a triangle. So that's another one of those keywords we need to know. So we've seen centroid today, which is going to be the point of concurrency of the
medians,
and the orthocenter is the point of concurrency of
the altitudes. And we still also have circumcenter and incenter involving angle bisectors and perpendicular bisectors.
Yes.
4 different point of concurrencies that we got to remember.
And these are the 4. So
that's it. Okay.
That's it. We're good.
Phew.
But we do need to know these. And we
Okay.
need to know the relationships that exist here. And that's why there's a lot to this. A lot to this chapter.
Okay.
At least the first 3 sections of this chapter that we really need to be careful with. Now, the location.
All right, so we didn't put it. Notice with the centroid, they were all located in the somewhere inside the triangle. you guys explored this today. The location of this orthocenter, just to recap, this is an acute triangle. Notice where it's located.
Inside.
It's inside. And let's go down to here. A right triangle. Whoops, I don't know what I was thinking there. Right triangle is located.
It looks like it's located on the triangle, but it's located at the right angle, too. At the vertex.
So it's at actually the vertex of right angle.
Yeah.
So it's right there. And the reason why is because notice when you draw in the altitude, the blue segments here, if you're drawing from a vertex to the opposite side and being perpendicular, it ends up being one of the sides, the leg of that right triangle. And the same here. This also ends up being a leg of the right triangle. The only altitude that actually goes inside is the one where you go from the vertex of the right angle to the other side.
To that hypotenuse.
So this one is an obtuse triangle. And where is it located?
It's located outside. And this kind of goes along with that idea of that's where we're going to have to draw those perpendicular segments that are all outside of the triangle. But if you continue them on, then you would be able to see that point of concurrency.
So the sides of the triangle, let me highlight. These are the kind of more the solid white lines. I'm making them green now. And if you draw just the segment here, it kind of stops there. This one stops here. This one stops here. But we know that they are going to be concurrent, so if you extend them out, they're going to eventually intersect outside.
Right.
Knowing the location of all your point of concurrencies are going to be important. Because Ms. Hokami, I might ask you, okay, well, tell me where the point of concurrency or where the circumcenter is located in a right triangle.
Yeah, and I would have to know that it's on the hypotenuse. And these would be good sometimes always never questions, too.
Exactly.
Where a point of... the orthocenter is located inside the triangle. Well, is it always, sometimes, or never?
Yeah, so it would be
knowing.
Sometimes,
depending
on the triangle. Exactly.
All right, and the theorem, this is the easiest theorem you're ever going to learn. The theorem of the of the concurrency of the altitudes of a triangle is just that the lines containing the altitudes of a triangle are concurrent. There is really no special relationship here. We've taken a look at the circumcenters and talked about that point of concurrency was equidistant to all the vertices. We took a look at the incenter and said that that point of concurrency was equidistant to all the sides of a triangle. We took a look at the medians and we realized that that centroid was that 1/3, 2/3 relationship with all of those from that point of concurrency, from that centroid to all the sides and to the vertices. This one, no special relationships.
Okay, that's somewhat nice. Just basically means that we can't really use the altitudes a lot for, I mean, the big fit reason to know altitude of a triangle is a lot of times to find the area of it, which doesn't really, it's not what we're going to focus on today.
But they are all concurrent lines, so that's something special, and that point of concurrency we do have, it's called the orthocenter.
All right, so let's try to apply some of these concepts. All right, so this one has lots of questions. Let's start, first of all, and I think this first question is kind of an important one for when you get tested or quizzed over these concepts. The first thing what you want to ask yourself is what type of segments are in the picture.
Okay.
Right, so looking at that picture, what would you say?
Okay, I do notice that the segments are hitting the sides of the circle at their midpoints. So I can tell that V, X, and M are all midpoints because of the way that the segments are marked congruent. So I'm thinking either perpendicular bisectors or medians.
Okay.
And looking at this, there's nothing marked perpendicular, but I do notice that those segments do all go to the vertices, so these are definitely medians.
I like your thought process there. Kind of narrowing down based on what the picture is giving you. This example is a great example because of the fact that it doesn't tell you what it is.
Exactly.
It communicates in the picture, so you have to understand. All right. So now that we know these are medians, that will tell us kind of some more things. So we got to feed off what we know about median. The first thing is, let's name the point of concurrency. What do we call that?
That is the centroid.
So just some vocabulary. Now that we know we have medians and we have the centroid, and the centroid actually is point C in this case.
Correct.
Right? So let's find some information about it. It says, let's say CG is 32.
Okay.
Right? So CG is 32. That's this segment right here.
Okay.
And it says find GX.
Which would be that whole median.
Okay. And find CX, which
Okay.
is this little guy right there.
Sounds good. Well, I know that with the medians, there's that 1/3, 2/3 relationship.
Okay.
And actually, the theorem said that CG, so going from the vertex to the median, that is 1/3, or sorry, that is 2/3 of the entire median.
So the whole entire median is that GX. So technically, the CG is 2/3 of GX.
Right.
Okay.
So just kind of pointing out those words. CG is, that kind of is our equals word. 2/3 of means 2/3 times that GX. Okay. So if I go ahead and take put just the values that we know in there, 32 is
All right.
my
So
CG.
32 is the CG.
So that is 2/3 of GX. So I can go ahead and just write that in, 2/3 times GX. So I can think about dividing by 2/3 or multiplying it by 3/2. And that should give
The
me
GX would be, I think, 48.
48.
Which obviously makes sense that it's going to be bigger because that
It's the whole
segment
thing.
is the whole thing.
Sure.
All right. So that's that particular length there.
Okay, then they also asked about CX. Well, I remember the 1/3 and 2/3 relationship, but I also know that if something is a third and another piece is 2/3, I remember that one was half of the other one. So really, CX is half of CG. And we knew CG was 32, so CX is half of 32. So that would mean that CX is 16.
Now, can you think of other ways you could have found the CX that we just found?
I could have, since I know that the GX was 48, I know that it's just a third of the 48.
Okay.
To me, I like dealing with halves better.
So you
but
could have done a
it
third
either
of
way.
48. You could have also, if you know this whole thing's 48,
Just
right?
subtracted. Yeah.
Do 48 minus 32. That would have gotten you 16. Could you have founded CX before you found GX? Well, yeah.
Sure.
If you know this whole thing is 32, you could have taken a half of 32 and gotten 16, and then you would have added these to get the 48. There's a variety of ways. So that's why knowing the different relationships, the three that we showed you, is helpful, but it's not like necessary.
Right.
You could do this a variety of ways. So the questions below
It's
is
not
just
necessarily to know all of them.
No.
As long as you know,
know one
some
of them.
Yeah.
If you know at least one of them, you're good to go.
Yes.
Now, the next two questions is kind of restating what Ms. Kirby's already mentioned. So what's the relationship between CX and GX? Well, we kind of said something earlier. Here's CX.
Yeah, CX was
and
1/3.
GX. So CX is a third of the GX, right?
Yes.
And then what's the relationship between CX and CG?
So CX was half of CG.
And you could flip flop that. If I said, what do I know about GX and compared to CX? Well, it's
So I would know GX was 3 times CX.
yeah. So you could say that GX is 3 times CX, and then you could say CG is.
2 times CX.
So it just depends on how you want to word it.
Okay. So this next one, all they tell us is that D is the centroid. We don't have anything marked on this picture. What is a centroid, Mrs. Palermo?
Okay, centroid is the point of concurrency of medians.
Okay, so if I want to just kind of start marking my picture so I know what that's telling me, what are medians?
Medians go from a vertex to the opposite side's midpoint. So that means we have AE and EB congruent, BF and FC, and all the way around.
Right.
Now, they're not necessarily all congruent to each other. They're just congruent within that segment.
Absolutely.
Or that side.
Yeah, absolutely. So we really need to know the vocabulary word there, that centroid. We need to know, okay, what kind of special segments are those, and what does that look like in my picture?
Okay.
Okay. We also know that BG is perpendicular to AC.
Okay.
Okay.
Which right away I'm noticing based on that, I know BG was a median, but I also know now it's a perpendicular bisector because it's also perpendicular to that side.
Awesome. And there's a lot of relationships we learned with perpendicular bisectors as well.
Now, are all the medians perpendicular bisectors then?
They don't tell me that, and we cannot assume.
Okay, so just BG is
Just
a perpendicular
BG.
bisector.
And just by one being a perpendicular bisector, that does not mean they all have to be.
Okay.
Okay. So now we've got all that marked in our picture. They tell us that BG, so going from B to G, that whole segment, is 18. And they tell me that AD, so just this part right here, is going to be 10. They ask us to find DG, AG, and the whole perimeter of the triangle too.
Okay.
Okay. I'm
All
going
right.
to let you think about this one for a
Okay.
second.
All right, I'm gonna just start kind of in order. Maybe that's because that's gonna help me. So
Okay.
I'm just gonna start with DG, and I look and I notice DG is actually on the median
Right.
of BG, and that's the good thing because they gave you what BG is. So I'm gonna ask myself, and I think back to what I just did, is that I know there's a relationship between DG and the whole median.
Right.
And it goes from the centroid to the midpoint. So it's a third of the whole median.
Great.
So I could say BG is a third of that BG, which is 18.
So DG is going to be a third of 18.
Or basically cutting that by dividing it by 3.
Exactly.
So DG is 6.
Okay. Awesome.
And I like that she labeled back in the picture because you never know. Sometimes when you find something, it could come in handy. So that's one piece.
Okay. So now next we're looking at AG.
All right. So I'm looking at AG, and AG is not on a median. It's a part of the side of a triangle. It's basically half of AC. But I don't know what AC is, so I can't do that. So I got to think about what I do know. They gave you AD as well. There's probably a reason for it. So if they gave me AD, I'm going to start thinking about what does AD and AG have in common? Well, we also found DG just now, which is the 6. Well, I noticed that they form a right triangle.
They do form a right triangle. And when you've got two sides of a right triangle,
You can use the Pythagorean theorem to find the third.
okay?
All right, so I'm going to use the Pythagorean theorem. There's not really any relationship with the AG and any of the other stuff. So I'm going to go ahead and use the Pythagorean theorem and say, well, 6 squared plus, I'm going to say that's AG squared. I'm just going to call it AG.
Okay.
Equals 10 squared.
Great.
And if you want to call that B or A, whatever,
Yeah.
it doesn't
We
matter
just
to
want
me.
to not lose track of what we're finding.
Yes. So that's 36 plus whatever AG is squared equals 100. And then I can say AG squared is equal to 64, which means AG is 8.
Yeah. And I know when I'm talking about a segment length again, when I take a square root, I could get plus or minus 8, but we'll never have that negative side length. So AG is 8. Okay, so we found DG and we found AG. That was 2 parts. And then they asked us to find the perimeter.
Okay, now I know because we've talked about perimeter before and you've done this in middle school too. Perimeter is the distance around a figure.
Right.
Which technically means if I know all the sides of a triangle, then I can add them all up. Now, I look at it and I know AG is half of one of the sides. So I can say GC is also 8, and which means the whole side AC, that whole side is 16. Now,
So there's one side.
does that mean all the other sides are 16 as well?
No, not necessarily.
Okay, because they didn't tell us it's equilateral.
No.
So I'm thinking, this is what I'm thinking. I gotta kind of think of the bigger idea here. I see that triangle ABC actually is made up of 2 right triangles.
Okay.
And the reason why I say that, because AB is part of that one right triangle, and then BC is part of another right triangle. I'm just going to focus on one of them.
Okay.
The reason why I did that is because technically in that right triangle, I have the whole side of BG and the whole side of AG.
Right.
And the reason why I'm pointing that out is just something we just did. If I can find AB by using the Pythagorean theorem again, all right, I can find that AB.
Okay, so I'm just going to draw this triangle that we're finding. We've
like
got
that idea.
This is our B, this is our G, and this is our A. And we know that this was 8, and we know that this was 18.
That's so much easier to see. Okay.
So we're going to find
AB. All right, so I'm going to use Pythagorean theorem. This time, that's the hypotenuse. So I'm going to say 8 squared plus 18 squared is equal to, I'm just going to call it C. So C squared. So I know you're making a comment about that being AB.
I'm going to call that C for right now on my picture, just so we know where it goes.
Yeah.
Okay.
So that's 64 plus, 324
Equals our C squared.
And when I add that up, get my calculator, 388. And then when I take the square root of 388, I get, now, this is not a perfect square. So is it okay that I round on this one?
It's okay that we're going to round right now.
Okay,
Because
okay.
we haven't really, so we're going to say it approximately equals what?
Okay, I'm going to say, let's do to the nearest 2 decimal places, which would, if I look at my calculator, it says 19.6977, blah, blah, blah. So I'm going to put 19.70 is that side C, which is side AB.
So we know this is 19.70. Okay, now, we could repeat that whole process, right?
Yeah, because the other triangle BGC is a right triangle with
The same
two
two legs.
legs, which
So
I don't need to do that. So
don't
that
need to redo
means
that.
BC is also 19.70. But you know what? Something I mentioned earlier.
Uh-huh.
You remember me saying something about BG being the perpendicular bisector?
Uh-huh.
And I know that any point on the perpendicular bisector of a segment is equidistant to its endpoint. So technically, we know BC and BA are going to be the same length.
Love that you mentioned
So
that.
this is an isosceles triangle.
It's an
in a
isosceles
sense.
triangle. Okay, so then how do we find the perimeter of triangle A, B, C? And I should maybe do a little p, just so that way, or smaller p, so you can tell what it was.
We're just going to add up the 3 sides. So that means we're going to add up 16 and then 19.70 basically twice.
And what's
And
that going to
that
give us for our total perimeter?
totals, let me figure it out.
Now, by the way, I know that we rounded this 19.70, but if it's already in your calculator, could we just leave that big long decimal in your
Yeah,
calculator?
and that's what I did. I did.
Yeah. So then if you leave that big long decimal in your calculator and maybe say times 2 first,
Uh-huh.
and
And then add 16.
add 16, what is that perimeter?
It
that way
gives
us a little
you
closer.
it gives you about 55.40. Now, sometimes that will actually be that case if you type it in again, but sometimes it won't. So you just got to be kind of cautious about that.
Yeah.
One more slide. It says, where is the orthocenter? Oh, before I forget, that last question, there's the bell again. That last question would be an excellent quiz or test question.
Oh, yeah, it would.
It's a very multi-step, kind of thinking about what you know, the vocabulary,
And really applying what you know.
applying stuff. Yes. All right. So orthocenter is what we're focusing on here. It says, where's the orthocenter located in triangle ABC? Now, I don't have a picture drawn. I can draw some pictures. They have 3 scenarios. All right. So when you think of orthocenter, what are we thinking?
We're thinking altitudes.
And if we're thinking altitudes, we know where an altitude's orthocenter is located when it's acute, right, or obtuse. So that's really kind of what we're focusing on.
Okay.
So the first one is, what if A and angle B and angle C all have the same measure in a
Okay.
triangle?
So that would mean that it would have to be an equiangular,
Okay.
which is also equilateral. We've taken a look at that before.
Uh-huh.
And so that would be an acute triangle.
So this would be an acute triangle. So kind of get a visual of that, which means it's located where?
inside the triangle. And guys, if it helps to draw the pictures for these, you're welcome
if
to
you
do
need
that.
to, you know,
We know
this
they're
is
all
A,
60
B, and
degrees.
C. Yeah, if they're all the same, then they all have to equal 60, which means acute. All right, what about this one?
For B, I'm noticing that A and B were both 45.
And
So
I'm just
okay.
drawing a sketch. So if these are both 45,
That would mean that together they're 90. So that means C would have to be 90. So that's a right triangle.
all right. Again, you don't have to draw a picture to see this, but so where is it located on the right?
And a
triangle?
right triangle was located on the triangle, and it was located at the right angle, at the vertex of the right angle, so at C.
So it would be actually at point C in a sense.
Right.
Right? If you just said on, probably be okay, but sometimes they might ask you to be a little more specific. So make sure you're careful with that. All right, what if angle A is 110 degrees? So I'm going to make a picture and try to make it look a little bit.
Okay, so I'm thinking angle A, if it's 110, that's definitely an obtuse triangle.
Yeah, don't need a visual for that.
And obtuse triangles are located outside. And guys, that's about as much as we can really ask you about orthocenters, just because there's not really a special relationship among them.